So the video we're going to show now actually goes back to, again, Stephen Kotler's comment about that part of your brain that is hypercritical, that tells you you're not enough of this, or you need to be more of that, or this isn't right about you. And I think you'll see in this video with Rosie King that we're all okay.
I haven't told many people this, but in my head, I've got thousands of secret worlds all going on all at the same time. I'm also autistic. People tend to diagnose autism with really specific checkbox descriptions, but in reality, there's a whole variation as to what we're like. For instance, my little brother, he's very severely autistic. He's nonverbal, he can't talk at all, but I love to talk. People often associate autism with liking maths and science and nothing else, but I know so many autistic people who love being creative. But that is a stereotype, as the stereotypes for things are often, if not always, wrong. For instance, a lot of people who think autism and think Rain Man immediately. That's the common belief that every single autistic person is Dustin Hoffman, and that's not true. But that's not just with autistic people either. I've seen it with LGBTQ people, with women, with POC people. People are so afraid of variety that they try and fit everything into a tiny little box with really specific labels. Like, this is something that actually happened to me in real life. I Googled autistic people are, and it comes up with suggestions as to what you're going to type. I Googled autistic people are, and the top result was demons. That is the first thing that people think when they think autism. They know. One of the things I can do because I'm autistic, it's an ability rather than a disability, is I've got a very, very vivid imagination. Let me explain it to you a bit. It's like I'm walking into worlds most of the time. There's the real world, the world that we all share, and there's the world in my mind. And the world in my mind is often so much more real than the real world. It's very easy for me to let my mind loose because I don't try and fit myself into a tiny little box. That's one of the best things about being autistic. You don't have the urge to do that. You find what you want to do, you find a way to do it, and you get on with it. If I was trying to fit myself into a box, I wouldn't be here. I wouldn't have achieved half the things that I have now. There are problems, though. There are problems with being autistic, and there are problems with having too much imagination. Like, school can be a problem in general, but having also to explain to a teacher on a daily basis that their lesson is inexplicably dull, and you are secretly taking refuge in a world inside your head in which you are not in that lesson, that adds to your list of problems. Also, when my imagination takes hold, my body takes on a life of its own. When something very exciting happens in my inner world, I've just got to run, I've got to rock backwards and forwards, or sometimes scream. This gives me so much energy, and I've got to have an outlet for all that energy. But I've done that ever since I was a child, ever since I was a tiny little girl, and my parents thought it was cute, so they didn't bring it up. But when I got into school, they didn't really agree that it was cute. It can be that people don't want to be friends with the girl that starts screaming in an algebra lesson. And this doesn't normally happen in this day and age, but it can be that people don't want to be friends with the autistic girl. It can be that people don't want to associate with anyone who or can't fit themselves into a box that's labeled normal. But that's fine with me, because it sorts the wheat from the chaff, and I can find which people are genuine and true, and I can pick these people as my friends. But if you think about it, what is normal? What does it mean? Imagine if that was the best compliment you ever received. Wow, you are really normal. Compliments are, you are extraordinary, or you step outside the box, you're amazing. So if people want to be these things, why are so many people striving to be normal? Why are people pouring their brilliant individual light into a mold? People are so afraid of variety that they try and force everyone, even if people who don't want to or can't, to become normal. There are like camps for LGBTQ people or autistic people to try and make them this normal. And that's terrifying that people would do that in this day and age. All in all, I want to trade my autism and my imagination for the world.
I meant to say, you're okay just the way you are. I think she makes such a great point. Does anyone ever compliment you on being normal and being in the box? Hell no. Now, I know it seems like Aspen Brain Lab just flows seamlessly without anybody behind the curtain, but in fact, we have a terrific board. Glenda Greenwald, of course, is the president and founder. But the chairman of our board is Sharon Handler-Loeb, and she's going to introduce our next speaker.
Well, first of all, it's just amazing as the years pass to see this room fill up with people who are interested and care about what's going on with the brain. Another frightening illness which affects millions of people every year is depression. And our next speaker is one of the warriors who is fighting this illness. His name is Dr. Joshua Gordon, and he is an award-winning psychiatrist and neuroscientist from Columbia University, who is a distinguished member of the Depression Task Force of an amazing foundation called the Hope for Depression Research Foundation. As a member of this task force, his research is part of a collaboration of leading brain scientists from the United States and Canada, and their work aims to find the causes of depression and set the stage for the development of unbelievably needed new medications and treatments. So I'm glad to welcome Dr. Gordon.
Thank you so much for the introduction. Thank you to everyone who helped organize this event, for bringing me to Aspen for the first time. It's truly beautiful here, even in the rain yesterday. It was a beautiful rainbow I hope people got to see. Of course, if you're depressed, you can't always enjoy those things. And I think it's almost unnecessary to explain what depression is, because I'm sure that everyone in this room has been touched by it in one way, shape, or form. But depression is more than just feeling sad. It's feeling sad to the point often of despair and hopelessness. And it's accompanied by a range of symptoms which indicate some sort of physiological as well as psychological disturbance. So it includes things like sleep and appetite disturbances, weight loss, weight gain, physical slowing or agitation, fatigue, loss of energy, and of course, as well as difficulty concentrating, which all indicate various failures of brain systems. Of course, it's also accompanied by things like thoughts of death and suicidality, which can be, although not the only way you can lose your life from depression, perhaps the most common one. Depression is a tremendously burdensome disease. It's highly prevalent, so that it affects about 20 million people in the United States each year, and it is the primary cause, although not nearly the only cause, of suicide. Just to give you a little bit of a flavor, 1 in 10 teenagers will be affected by depression sometime between the ages of 13 and 18. 1 in 10. That's what I mean. That's one of the reasons why I know that each of you has been touched in one way, shape, or form by this disease. It is tremendously costly. It's a leading cause of disability for young people ages 15 to 44. It has an estimated economic impact of over $70 billion, $12 billion of which is just in lost work days. And one of the reasons why it's so expensive and burdensome is that it afflicts us when we are young and never goes away. Worldwide, it's the second leading cause of disability and will be the leading economic global health burden by 2030. So again, something like 1 in 8 persons will have a depressive episode some point in their lifetime, and 1 in 10 of those will attempt suicide. And despite it being a disease which carries this tremendous burden both for individuals who suffer from it and for society who has to pay for it, we don't have really good treatments. We all know Prozac and many other successful treatments for depression, but although these have been successful and really a revolution in the care of patients, they are at best partially successful. So this is a curve of patients given a Prozac-like drug, and it goes, the scale here goes, or should go from, well, there you go, from 0 to 1. This is the proportion of patients who are well after a certain amount of time on the drug or on the placebo. And you can see that the drug does better than a sugar pill, okay? Sure, it's effective, but at best, even out here of 12 weeks of treatment, nearly half of patients have not recovered from the illness. Depression is an episodic disease, though, so eventually most people who have a depressive episode will recover, whether on a drug or off. After recovery, though, the risk of having another episode is tremendous. This is a lifelong chronic illness. So this is a curve of people who are successfully treated for depression, who stay on the drug for 6 months or longer, and then their medicine is stopped, and or I should say their treatment includes all kinds of treatments, and this is the rate at which those people will go on to have at least one more depressive episode. So you can see by 3 years, nearly half of the people will have had another episode, and by 10 years, fully 3/4 of people who have a single episode will have a second. So it's a lifelong disease with tremendous costs and burdens and inadequate treatments, and not surprising in this day and age, but actually through all of the history of the NIH, it's an underfunded effort. As a result of little research, so this is a curve, this is just a demonstration on the y-axis of the amount of funding that the NIH gives for a given illness, and on the x-axis, the burden in disability. And in this black line here represents sort of an inadequate, probably, but fair distribution of funds based upon burden of illness. And you can see depression here is one of the most burdensome and well below this sort of fairness line. The dollars that are spent on depression research are not representative of the burden it presents in society. And as a result, perhaps, of this underfunding, there is no truly known causes beyond saying things like stress. There's no known diagnostic tests. There are no new medications, fundamentally new mechanistic medications since the 1990s. And there are no clear neurobiologic mechanisms. So despite the tremendous burden, we don't know a whole lot about the disease, and we treat it inadequately. So that said, why? Why is it so difficult to crack? Because we are now spending millions of dollars on depression research. One of the reasons why the disease is so incredible to crack is because it's a disease of the brain. And the brain has incredible complexity. There's some 86 billion neurons. Each one of those connects with thousands of partners, so that there are literally trillions of connections all over this brain. And not only that, those connections are not static. They're not wired in like an integrated circuit that you feed the electricity into and it just runs. They're constantly dynamically changing on all sorts of timescales, millisecond timescales, seconds timescales, and we heard about Alzheimer's disease and aging, of how the nervous system is changing on years timescales. So all these things add to the complexity and the difficulty of understanding. Now, we heard this morning from Walter Isaacson about what makes innovation possible, and the first thing that he said was creativity. And we have lots of creativity, fortunately, in the neuroscience field. Lots of individual labs that are all working on different parts of the brain or different functions of the brain or different diseases of the brain. And although there's a lot of collaboration in scientific meetings and things like that, basically the person who runs the lab is the individual principal investigator, the individual faculty member working with a team of small as a few people to as large as 30 or 40 that are making all their scientific decisions individually based upon what's best, yes, for their research program, but also for their careers and their families. And one of the things that creates is a lot of great creativity, but missing the second element that Walter mentioned of innovation, which of course is collaboration. And so realizing this, the Hope for Depression Research Foundation recruited a bunch of depression neuroscientists to start working in a different model. Instead of independently in their own labs making hypotheses, designing experiments to test them, they decided that we should all work together, actually, that we should design a research program that's not individually lab-based, but really quite collaborative. And that program is the main thing that I want to tell you about today. I would love to say that we have answers for depression from this research program, but it's really a work in progress. But I want to give you a sense of the power of that work in progress by perhaps exaggerating the sureness we are about some of the results, but just to show you how this process can lead to some definitive hypotheses and hopefully new treatments for depression. And so to do that, I'm just going to walk you through some individual results from individual labs that have come out of this collaborative research program. And I'm going to start with someone who many of you may have heard of, Helen Mayberg, who really pioneered a new treatment for depression called deep brain stimulation of the medial prefrontal cortex. So Helen was working, actually, she's a neurologist actually, but she was imaging patients with depression, and she noticed that a particular part of the brain, the medial prefrontal cortex, which is along the middle of your brain, medial, right, and prefrontal meaning it's in the front. And it's been known to be important in lots of processes, including controlling your emotions, and she found that activity in this area was elevated in patients with depression, and that regardless of what kind of treatment, whether it was psychotherapy or electroconvulsive therapy or medication therapy, patients, when they got better, the activity in this brain region goes down. And she realized, of course, from lots of years of work in Parkinson's disease, that an effective way to decrease activity in the brain region is to electrically stimulate it very powerfully, so that essentially you're shutting down its ability to generate its own activity. And so she persuaded an intrepid neurologist, a neurosurgeon, I should say, to implant electrodes and deliver brain stimulation in the medial prefrontal cortex, and she's found that stimulation there helps a certain percentage of patients who have otherwise intractable depression, so part of that 50% of patients who are not getting better. Now, the HDRF, of course, seizes on this and decides, okay, well, what other parts of the brain are going to be working? No part of the brain works by itself. The medial prefrontal cortex is not an island. It's communicating via these trillions of connections with others. So can we expand upon that knowledge and identify other brain regions that are involved in depression? So Michael Meany had long known that early life stress, which is one of the few known risk factors for depression, early life stress damages the hippocampus. And it makes, in particular, the hippocampus, actually that brain region that was talked about earlier in relevance to Alzheimer's, that's also relevant for depression, makes that hippocampus more susceptible to stress later on in life. It actually does that through an epigenetic mechanism, by the way. So it makes the hippocampus more susceptible to stress later in life. And another member of the Depression Task Force, Bruce McEwen, had shown that hippocampal neurons actually later in life are damaged, physically damaged by stress. Their connections shrink. And he also had showed in additional work that the medial prefrontal cortical neurons as well shrink. And another brain region called the amygdala, which is responsible for a lot of negative emotion like fear, the neurons in the amygdala actually increase in size. They grow. So stress is not uniformly bad for the brain. Stress is not causing bad stuff happening all over. It's bad for certain parts of the brain, like the hippocampus, the prefrontal cortex, and pro-growth for other parts of the brain, like the amygdala. So we're starting to see that the potentially the emergence of a depression-related circuit, and we can add a little bit more to that. Eric Nestler showed that chronic stress, which we know now damages the hippocampus, and the amygdala actually, and enhances the amygdala, actually induces in animals a depression-like state that's very similar to that seen in patients. Moreover, Eric showed that a particular other brain region, the nucleus accumbens, is number one, also damaged by stress, and number two, that this stress changes the relationships between the nucleus accumbens and other brain regions in terms of the genes that these brain regions are using collaboratively. Renee Henn also showed that the same stress paradigms alter gene expression in these other brain regions. So each of the members now has contributed to the identification of an emerging circuit for depression. Now, in my own work, what I've done is recorded from these brain regions electrical activity during models of depression. And what we've found is that these brain regions all enhance their activity, just like Helen showed in patients, but also increase the degree to which they are working together, they're collaborating together, they synchronize more with each other. And I'm just going to show you how we do that, because why not? I'm a neurophysiologist, you might want to know what a neurophysiologist do. So we take animal models and we implant electrodes into the parts of the brain that we think are interesting. So in this case, in the hippocampus. And we can record the activity of neurons in the hippocampus. And it turns out that those neurons are not just, simply doing random things. They actually fire rhythmically over time. Okay, and so this is just a curve of neuronal activity that I recorded from the hippocampus some years ago and stuck on this slide, and it's stayed with me ever since. But now I have graduate students and postdocs doing it. It goes up and down in the hippocampus, and this time scale is about a second, so it goes up and down about 8 times a second. We call this an oscillation, or a theta frequency oscillation. And we can also record activity simultaneously with another electrode. Sorry, in blue, that's the oscillation, and with the other electrode come up, yeah. And so now we can record activity between the 2 brain regions simultaneously, and lo and behold, they're going up and down together. Not precisely together, but more or less together. So if we line up the peaks, you can see these arrows are, slightly different in angle. The peaks are offset and not quite precisely aligned, but we can actually quantify the degree to which these 2 brain regions interact together. And what I can tell you is that during anxiety, these 2 brain regions synchronize together more strongly than they do, during depression, than at baseline. So now we have these different elements of the circuit that have been identified by various other members, and when we record from them, we can see that they're all working together more strongly during depression. Does that mean we can do anything about it? So one of the first things that we've done, and this is done by a number of members of the group, is shaking these models and deliberately altering activity to try to treat a depression-like state. So I'm just going to give you one example of work that was done actually by Eric Nestler's group at Mount Sinai. And it's to try to break this one part of this connective circuit, which is the inputs from the hippocampus to the nucleus accumbens. And so what we can use is these advanced technologies that have been really revolutionizing neuroscience lately. How much time do I have? We're okay? 5 minutes. Oh, good. So, so it's called optogenetics. And what optogenetics is a way we can artificially change the brain to make neurons, instead of responsive just to other neurons, we can actually make those neurons responsive to light. And you'll see why that's useful in a minute. What we do is we take a virus and we inject the virus into the, say in this case, the hippocampus, and that virus carries a gene for a protein which is normally not found in our animal models or in humans. It's found in bacteria. But bacteria use that protein to respond to the environment, and one of the important things about the environment that protein is responding to is light. And so we can take these neurons in the hippocampus, which normally shining light doesn't do anything, and we can control them, remote control them by little pulses of light. Now, that protein is expressed in neurons from the hippocampus. They send axons, one of the many connections they make through axons, down to the nucleus accumbens, and we can take a little fiber optic, just like the fiber optics that are used to, carry telecommunications across the universe, carry the internet. We can take a little fiber optic and implant it into the brain and shine it just on the terminals of the hippocampal neurons in the nucleus accumbens, and we can turn on those terminals or turn off those terminals at the touch of a button, or actually more likely at the control of a computer program, which so far has not achieved singularity, thank God. And we can then ask, what effect does that have on depressive-like symptoms in our animal models? And just like Helen showed in the medial prefrontal cortex, we can treat, if you will, the depression-like state in animals by silencing these neurons here, in these neurons as they project from the hippocampus to the nucleus accumbens. There's a lot of things we could think about to harness similar technologies in humans, but the point of it mostly is just to say that now that these kinds of experiments help us establish this circuit. One other way, this circuit is being important for depression. One other way, and this is best exemplified by some work by Huda Akil, to affect this circuit is genetically. So you can either breed animals genetically, which is one thing Huda's been doing for years and years, or manipulate them by putting genes into any one of these brain structures and ask what is the effect of that on depression-like behavior, yes, but also on the kinds of patterns of activity that we can study in the circuit. And so we can learn, therefore, sort of what molecules govern these patterns of activity. And we need molecules because molecules are one of the easiest things to target with pharmaceuticals. Although one could argue that we can target activity in the circuit with devices like deep brain stimulation or transcranial magnetic stimulation, for those of you who heard those devices. But we do have a member in the group who's a magical medicinal chemist, Jonathan Javich, who's helping design medications that might target these kinds of patterns of activity that we're noticing. So what you get in the end is an intense collaboration that involves something really different than the normal scientific process, collective planning of experiments. We meet in person at least once a year, and actually twice a year, and on the phone once a month, where we're actually saying, okay, this is the state of the experiment. What's the next experiment that needs to be done? And it doesn't matter if it has to be done across all the labs or in a handful of the labs, but we want to make sure that we're all attacking the problem with the same collective effort. It involves data sharing, so all the data is uploaded to a data center that's in the University of Michigan, and everyone in any of these labs can get access to the data the moment it's discovered, not published, but actually discovered, so that we can all work together. And the focus of our group anyway is really on the neural circuit, so that we can use cutting-edge neuroscience technology, and it gives the promise of novel interventions. And so with that close, I just want to acknowledge that the support of the founder of the foundation, Audrey Grusin, her husband Martin, and lots of HDRF donors who give money that essentially goes right to us, the scientists, but with a catch, that we work together to try to build, go beyond creativity, if you will, and move into collaboration. So thank you.
So I have a quick question, and that is, what do you think is the best treatment for depression at the moment?
Well, that's a hard question and an easy question. The hard part is that no individual treatment has been proven to be better than any other individual treatment. But the reason that's easy is that you need, I think, a combination of treatments. So exercise was mentioned before as promoting the growth and protection of neurons in the nervous system. Exercise is a fantastic antidepressant. So is a regular sleep cycle, so is social support and social exposure, so are medications, and so are psychotherapy. And no one medication has, to my knowledge anyway, been proven better than any other medication. The only thing that works better than anything else is actually electroconvulsive therapy, which has, instead of a 50% chance of getting you better, something like an 80% chance. So, yeah, I know it's surprising because it's a controversial treatment. It actually works, it works better. So, in conclusion, if you have a person who's depressed, a holistic approach is going to be the best approach. And there are probably dietary approaches as well that work. I'm just not as familiar with them.
We're just about to have a break, but we have one. Pete, you're going to come up soon. We're going to have an exercise snack in a minute, it is going to last 3 minutes, and then we're going to have a breakfast brain break. One sentence. It's estimated that 5.3 million deaths a year are caused by physical inactivity, which is about as many as are killed by smoking. So in order to escape this fate and to give you a little break, we are asking Pete Holman to come up, a strength and conditioning coach and the inventor of the TRX RIP trainer. Pete, you're all going to...
How come everybody's leaving? All right, do we have Mike? Can you guys hear me? How about these presentations, you guys? Mike, let me tell you something. My creative brain is buzzing right now. And Stephen Kotler got me thinking, as a presenter, before you present, how do you get your flow? So I thought, and then it came to me. Bruce Lee. Bruce Lee once said, empty your mind. Be formless, shapeless like water. You put water into a cup, it becomes the cup. You put it into a bottle, it becomes the bottle. You put it into a teapot, it becomes that teapot. Now water can flow, or water can crash. Ghosts! Be water, my friend. I got my flow going now. You guys, my name's Pete Holman. I'm a physical therapist and strength coach in town and a former U.S. national Taekwondo champion and team captain. My whole career has been about movement, but not just movement for movement's sake. Purpose-driven movement, movement with intent, movement with focus, movement with direction. And when you move with intent and focus and direction, there's a cognitive component. So we're going to do an exercise snack today that involves cognition. But before we do that, we've got to arouse the sympathetic nervous system. Now, in my opinion, the sympathetic nervous system kind of gets a bad rap. You get these hormones like cortisol, epinephrine, norepinephrine coursing through your body. They're actually good hormones in moderation, right? They help increase your heart rate, your respiratory rate. They give you cognitive function like Spider-Man, spider senses. So we're going to get our spider senses going. I need everybody to stand up. Everybody stand up. Now, we're going to do a drill called the Aspen Brain Lab Wolf Pack Howl. You heard me right. Now, I know there's a lot of conservatives in here. I know a lot of people are intellectual here, but set your egos aside. Let your inhibitions fly away with the wind, because we're going to howl at the moon. If you don't know how to howl, it's very simple. It comes kind of from this area, the visceral organs. Ow, ow, ow! Okay, now, oh my gosh. Ow, ow, ow! Guys, I've got chills right now. All right, we got our flow going. Okay, here's the exercise. Now, we're going to do something called the wave. And I'm not talking about the aloha wave, right? I'm talking about the drunken, obnoxious Sunday football wave that you see in the stadium. So here's what we're going to do. Everybody knows this. Whoa, right? Here's what we're going to do. We're going to start out with purpose-driven movement, though. I want everybody in what's called the universal athletic position. So separate your feet a little bit. You need to flex at your ankles, your knees, and your hips. I want you to put your hands on your thighs right here. Notice my spine is not in flexion. It's in a neutral position. From here, all we're going to do is extend up from the ankles, knees, and hips, wave our arms up towards the ceiling, and then come back down. Okay, try it again. One more. Up and down. Okay, now relax a second. In my opinion, exercise should have three components. Okay? There should be a big movement pattern, like the wave. There should be cognitive focus, and it should be fun. So here's the exercise. We're going to start on this side of the room. Everybody's going to be in that universal athletic position, UAP. This side of the room, I'm going to count down 3, 2, 1, go, and they're going to wave, and we got to have a beautiful symmetrical wave from right to left. Okay? Once it hits the left side, everybody's down in that UAP, and then we're going to go left to right. You guys got it? You've got to look out of the peripheral vision to your right and watch. The second the right side goes, the next person goes, and so on down the line. You guys ready? Okay, universal athletic position. Hey. I actually like that. Gigi says we're howling, so we're going to howl. I actually like that. So let's do a little audible, whoa, like you do the wave. Okay, here we go. Universal athletic position. In 3, 2, 1, go. Fantastic. Everybody down. Now we're going to go left to right. Ready? 3, 2, 1, go. Okay, now hold on a second. Everybody rest. Everybody gives me a hard time for not doing any social media. So guess what? The stakes are heightened now because this is going on my Facebook. We've got to up the ante a little bit. Okay, everybody in the universal athletic position. Okay. Oh, well, hold on a second. Video, we got this. Hey, Pete Holman reporting from the Aspen Brain Lab 2015. We got a captivating audience here. We're going to do an exercise that involves focus, movement, and fun. Are you ready, Aspen Brain Lab? All right, in 3, 2, 1, go. Big round of applause, big round of applause. All right, guys. Hey, thanks for joining. Just to summarize, we've now learned how to howl at the moon and do a drunken wave. So how's that for intellectual stimulation? If you're around this afternoon, don't miss my session because I'm going to teach each and every one of you how to transform yourself into a superhero. Thank you, guys.
It's time for, wait 1 sec. It's time for a healthy breakfast brain break, but do me a favor because it's really hard to feed 350 people in a half hour. This side of the auditorium, please go out that door. There are 2 stations with delicious breakfast. This side of the auditorium, please go out the front here and make a left. There are 2 different buffet stations. And please come back within a half hour on time, please.